Okay, can you hear me? Yeah, okay.
Yes.
So
Yeah.
this is going to be my last suggestion for seminar related to massive stars, I promise, because we had in December Logan, Mahi, and then Atira Menon, and Tomer will be the last. I try to find young people from the massive star crew to give you an overview of what they are doing. And I'm very happy that Tomer accepted my invitation because I was remembering the other day that he sent me a mail when he was a student in Potsdam, and this mail was lost forever in my inbox. I never answered back, so sorry.
I
I'm
still
very
don't know
happy
the
that,
answer to that email, by the way.
yeah,
We
yeah,
should
we
talk
can
about
talk
this.
about this at some point. Yeah. So thank you very much for accepting my invitation. Tomer started his studies in Haifa, Israel, in physics and mathematics. And then in 2011, he moved to Potsdam in Germany to do the master and the PhD. He finished in 2017. And after that, he got one postdoc position to work together with Hugh Sana in the ERC project to study binaries. And he has been there for a while. And I just learned a few days ago that he has been recently awarded with a Marie Curie Fellow at the University of Amsterdam to start soon in October. So congratulations for that. This is a very promising research line, and also your work is being impressive. So we are very interested in knowing about your research. His main line of work for people attending is Wolf-Rayet stars, as you will see today, model atmospheres and evolved binaries. And I like very much the way he summarized his career or his strength. He said that he's a driven and productive world-leading expert for spectroscopy of massive stars, binaries, and multiple systems. So looking forward to hearing from very interesting things that you are going to tell us.
Thank you very much. You always have to exaggerate a little bit in CVs,
Yeah.
so I'm not comfortable with this, but thank you for the kind introduction, and I'm happy to meet you all, even though it's virtual. I would have much preferred to be there in person, of course. And yeah, so today I'm going to talk about stars, so indeed, brace yourselves. And I will talk about quite unique stars, stars that are not like most stars, stars that are on the hot side of the Hertzsprung-Russell diagram, and you'll soon see what I mean. And they come in different types and shapes. Some of them are Wolf-Rayet stars and some of them are strip stars. And I hope that by the end of the talk, you'll know the difference between all these types. But let me first start by placing these objects that I'm going to talk about in the more general and quite exciting field of gravitational wave astronomy. So I know that you come potentially from very different fields, but I guess most of you have heard of the fact that we are measuring more and more of these gravitational waves that are coming to us from the merging events of neutron stars and black holes in the distant universe. And this diagram is one of the key diagrams that have been produced from this research, and it's constantly being updated as more and more observations are flowing in. And in case you've never seen it, what you see on the y-axis are the masses, and on the x-axis, there's no meaning. And down here are the neutron stars, up here are the black holes. And before we had gravitational waves, we only had access to the masses of neutron stars and black holes from their detection in X-ray binaries, in almost all cases. And in this case, the compact object would accrete mass from a nearby star and would emit very powerful X-rays. And the analysis of such objects would allow to put constraints on the compact objects. And you see the typical masses that were determined through this method, already revealing some kind of a gap between black holes and neutron stars, which is a focus of a lot of research these days. But what gravitational waves have done is primarily to populate the upper part of this diagram, where we are suddenly observing stellar mass black holes that are much more massive than we have ever observed before. And there's this entire research right now going on trying to understand how these black holes form, how do you even form these pairs to merge in the first place, what determines the mass distribution and the upper mass of these black holes. But we need to remember that these black holes, they form in the cores of very massive stars in the early universe. And in the early universe, one of the special things about it is that it's poor in heavy elements, it's poor in metals. So we say low metallicity environment. And this is one of the reasons why the field of massive star evolution at subsolar metallicity is now really undergoing a sort of a renaissance. And one of the reasons why we hear more and more about this subject. So I would like to take a step back and remind you what are these massive stars that produce these compact objects and what are their properties. And so first of all, we define massive stars as stars that start their lives with at least 8 times the mass of the sun, because we believe that such stars will undergo through all phases of nuclear burning until eventually they develop iron cores that will collapse into either neutron stars or black holes when the stars die. And because they produce all these heavy elements throughout their lives and finally through their supernovae explosions, we consider them to be a very important source of, for the enrichment of the universe in elements. But they're also very rare, and this is for 2 main reasons. First, the initial mass function. So the nature doesn't really like forming massive stars. It prefers forming stars like our sun. But also massive stars live a very short amount of time on their lives. So stars like our sun evolves over the scale of billions of years. Massive stars evolve over the scale of millions of years. So we have to work with limited samples in the field. But they make up for their rarity by being extremely hot and luminous. A single massive star can be more luminous than 1 million suns. And because of their high effective temperatures, they tend to be a very important source of ionizing radiation. They also tend to be a very important source of mechanical energy. This is both because of their final supernovae explosions. So these are some of the most powerful explosions we know, and this is how stars end their lives, massive stars. But also because the majority of massive stars are characterized by what we call stellar winds. So you see in this nice cartoon in the background, an outflow of material away from the star to the environment. And these winds are typically understood for massive stars to be driven by radiation. That means that the radiation that the stars emit gets absorbed in the outer layers and pushes the material away from the star. And these winds carry with them a lot of energy, so also mechanical energy. Really, you understand why we call massive stars cosmic engines, because they really can impact galactic scales in terms of their energy production. And they also happen to form these compact objects, connecting them to the gravitational wave astronomy field. So they really have a lot of synergies with many different fields in astronomy. And understanding massive stars really means understanding how they evolve from birth to death. And when we discuss the evolution of stars, we like to use this diagram here, the Hertzsprung-Russell Diagram, and you'll see those quite a lot in my talk. So get used to them if you're not. You see here the evolution of the luminosity and effective temperature of stars as they evolve over time. And here I'm showing you an example, kind of a textbook example for a 15 solar mass star. So such a star, it would do what all stars do throughout its life. It would spend most of its time burning hydrogen in its core. And we call such a star a main sequence star. And it would spend most of its time here until eventually hydrogen would be depleted in its core. And it would very quickly evolve to become a red supergiant, a gigantic, cool star that we observed many of. And this is how the star would look like about 10% of its life, burning mostly helium in its core, until eventually the star would collapse in a violent explosion, a hydrogen-rich supernova, leaving behind most likely a neutron star. But something quite different happens as you travel up the mass ladder. Significantly more massive stars, and where exactly we are not sure, but substantially more massive stars don't really like ending their lives as red supergiants, but rather prefer to go all the way here to very high effective temperatures before they end their lives. And the reason they do that is because they support such a strong mass loss throughout their lives. They have such powerful winds that they can actually strip themselves off these outer layers. And instead of seeing a cool, puffed up star, we see a hot hydrogen-depleted star. And we observe such stars. They're very rare, but we know of a few thousand of them in the galactic neighborhood. And they're called classical Wolf-Rayet stars. And I'll define them more carefully later. But for now, suffice it to say that classical Wolf-Rayet stars are these helium-burning hot stars that have very powerful stellar winds. And when we analyze them, we find that they're hot, they're hydrogen depleted. And because of that, we understand them to be these evolved phases of massive stars and the immediate progenitors of black holes. And so these are objects that are obviously objects that you want to focus on if you want to understand black hole production and other processes related to massive star evolution at the upper mass end. So this was the general picture, the textbook picture that we have for single stars. The problem that we have to deal with, and that's becoming an increasingly worse problem, is the fact that most massive stars are actually, they don't live alone, but rather in binary systems. So binaries may look like something like this. You would have the more massive star, the primary, and the less massive star, the secondary. And as the more massive star evolves, it evolves more rapidly. And it would want to expand. We've seen before that single star want to become maybe a red supergiant or something. But if it has a companion next to it, it cannot further expand. And instead, it would start transferring mass to this companion. And a lot of things can happen here. In this animation specifically, you have a stable mass transfer. So the secondary accretes all this mass, accretes also angular momentum. So it becomes a very rapid rotator. The primary star gets stripped off its outer layers, and it becomes something we call a stripped star. It could also look like a Wolf-Rayet star. Again, we'll talk about this soon. And if this stripped star is massive enough to exceed the Chandrasekhar mass limit, it may also explode as a powerful supernova, leaving behind a neutron star, for example, or a black hole. Eventually, such a system could become an X-ray binary. It could merge and become a Thorne-Zitko object. You could get runaway stars. And if you get a second supernova, you might even get a double compact binary consisting of 2 neutron stars or 2 black holes that may or may not merge. So you have such a big zoo of phenomena happening just by invoking binary interaction. So this is how it looks like in a pretty film, but how does it look like quantitatively? So we've seen this Hertzsprung-Russell diagram before, and we saw how a single star, say with 15 solar masses, evolves. If it's left alone, it wants to become a red supergiant. What happens if I now take a companion and put it in the vicinity of the star? Well, instead of becoming a red supergiant, suddenly there's something blocking it from doing it, and it would instead get stripped, and it would become a very hot star. And it gets stripped off its outer layers, and we see deep inside the hot and hydrogen-depleted layers of the stars. And in this stage, we call the star a helium star. Now, this star may take the form of, generally, if it's stripped in a binary, we call it a stripped star. It may also take the form of a Wolf-Rayet star, but for that, it would need to be significantly massive. And I'll show you later why that is the case. So this has been so far mostly theory. And the question is, do we observe all these different phenomena and all these exciting objects? And the answer is yes. And there are so many observational constraints from our galaxy and from nearby galaxies. But one of the galaxies I really like is the Large Magellanic Cloud, which is this dwarf galaxy not too far from our own Milky Way. It has a subsolar metallicity content, and we can study the massive star content in this galaxy in great detail. And it has been looked at by many different people and many different surveys, especially worth highlighting the Tarantula Nebula, which was studied really by a lot of people and contains a lot of massive stars. But we also have other regions that were studied in detail, and generally entire populations of different types of stars studied in this galaxy. And we are currently in the position to really collect all these different analyses and try and put them on a Hertzsprung-Russell diagram. And so this specific diagram was constructed by a colleague from Potsdam, Varsha Ramachandran. And when you just look at this diagram, it actually looks like, again, like a textbook example. You see all the observations here. You see the main sequence stars and the red supergiants and some blue supergiants and Wolf-Rayet stars, and everything seems to work out nicely. But when you start looking into the details, and no matter where you look, you find a lot of problems. And that ranges from the main sequence across the red supergiants, across the blue supergiants, and up until the Wolf-Rayet stars. So why am I telling you all of this? Because I'm not going to talk at all about all the problems that we have on the right part of this diagram. I'm only going to focus today on the left part of this diagram, the hot side of the Hertzsprung-Russell diagram. And one of the things I really like about Wolf-Rayet stars, or generally stars living in this diagram, is that they are really sensitive to whatever problems we have in our assumptions on the right side of the diagram, because whatever stars make it to the left side of the diagram had to go through all these processes that we have on the right side. And so there's this very nice citation from Kippenhahn stating that evolved stars are sort of a magnifying glass, revealing relentlessly the faults of earlier calculations. And this could not be more true for the objects that I'm going to talk to you about today. So now is the time for a more proper definition of Wolf-Rayet stars. And that's, if people are still listening, this would be important for me that people would also take with them, because there is a lot of confusion as to what Wolf-Rayet stars are. And this confusion actually causes caused some discrepancies in the literature that are not necessarily there. So what is a Wolf-Rayet star? A Wolf-Rayet star is a star that looks like a Wolf-Rayet star to an observer. And that means that its spectrum has a certain features, specifically these strong emission features that are broad, that would make an observer say, hey, I found a Wolf-Rayet star. An observer doesn't care what kind of an object that is when they find a new Wolf-Rayet star. So in other words, this is a spectroscopic class of objects. Okay, the detail is that H beta needs to be an emission, but that's a detail. But it turns out that for stars to have this kind of spectrum, what they really need to have is a very powerful wind. So all we know about Wolf-Rayet stars is that they have very strong winds, and these winds are characterized by a certain mass loss. So they induce a mass loss on the stars. The stars lose mass because of that. And I give you here the order of magnitude of these mass loss for Wolf-Rayet stars that we like to measure in solar masses per year. And I can imagine that some of you may not have a feeling for mass loss rates. So for comparison, our sun loses about 10 to the minus 14 solar masses per year. So we're talking about 10 orders of magnitudes larger than the amount of mass lost by our sun. We're talking about gigantic amount of mass loss. Okay, so why should stars start losing so much mass all of a sudden? Well, it turns out that stars lose a lot of mass when they approach the Eddington limit, this fundamental limit that stars are not supposed to exceed because otherwise they would explode from their own radiation pressure. And you approach the Eddington limit when the ratio of luminosity to mass grows. So how do you make it grow? You can either decrease mass or increase the luminosity. And indeed, these Wolf-Rayet stars, come in two main types. About 90% of the Wolf-Rayet stars are what we call classical Wolf-Rayet stars. They are stars that have stripped themselves off their outer layers by some process. For example, we've saw that binaries can do it. We saw that single stars can do it if their mass loss is strong enough. And then the result is that their mass goes substantially down. And so this ratio goes up and you get this Wolf-Rayet phenomenon. Okay, and these are understood to be helium burning objects, evolved objects that have already stripped themselves off their outer layers. About 10% of the Wolf-Rayet stars, however, are thought to represent a different class of stars, and these are the most massive stars in the universe. And they approach the Eddington limit not because of the fact that they lose mass, but because of their crazy luminosities. So the most massive stars have such high luminosities that already on the main sequence, while burning hydrogen, they appear as Wolf-Rayet stars. And in today's talk, I'm not going to talk about this class of objects. They are interesting if you want, for example, to probe the upper mass limit, to know how the most massive stars in the universe evolve. And just if you're curious, the current state of things is that our knowledge of the upper mass limit empirically is that we know that stars as massive as 150 solar masses exist. This is a robust limit, but it is also reported that stars as massive as 300 solar masses exist. This is less robust and relies on some assumptions. So this is just to satisfy your curiosity. But in today's talk, I'm only going to talk about this type of stars, the classical Wolf-Rayet stars. So to show you how critical this phase is in the evolution of a massive star is, I'm showing you here an evolution track for a 40 solar mass star in a metallicity that is roughly solar and slightly above solar. And down here, you see the evolution of the mass of the star. And you see that the star starts its life with about 40 solar masses, but ends its life with 10 or even 5 solar masses. And the majority of mass loss happens close to or during the Wolf-Rayet phase, which tells you how critical this phase is in determining the mass of the final compact object remnant, in determining generally how the star would evolve. And now, one really important thing to remember is that these mass loss rates, they're not some constant of nature, but rather they depend on the environment the stars live in. And so I'm comparing here on the left and on the right, the same star, a 40 solar mass star, but on the right, it's for a low metallicity environment, metallicity of about a fifth, something that might correspond to the small Magellanic Cloud. And you will see that the star on the right loses less mass. You can see it in the mass panel. You can also see by tracing the evolution of the star. So what happens here? As you go to low metallicity environments, you have less, the content of heavy elements decreases, but it turns out that these heavy elements are very important sources of opacity in the stars. And so as you decrease the metallicity, you decrease the opacity. And remember that it is the opacity or the absorption of radiation that is driving the wind. If you decrease the opacity, that means that you will not be able to launch a powerful wind with your radiation. And the obvious conclusion is that stellar winds should decrease, or the strength of stellar winds should decrease at low metallicity. And this is by now well confirmed, both observationally as well as empirically. And you can see the dramatic consequence that it has on the life of a star, this effect. So, for example, on the left here, you see that the star manages to reach the Wolf-Rayet phase. It manages to strip itself and become a Wolf-Rayet star. But here it doesn't really, kind of travels here on the coolish side of the diagram, and then that's where it ends its life. So we see that it's much harder to produce Wolf-Rayet stars at low metallicity from the single star channel, single stars. And so we had these two main channels to produce classical Wolf-Rayet stars. We either have stars that strip themselves by their own winds and eruptions, which is something I didn't talk about, or we have stars that can get stripped with the help of companions. And it's an ongoing question ever since the 60s that is still unresolved. Which of these channels dominates the formation of Wolf-Rayet stars that we are observing, and especially as a function of the environment they're in and the metallicity. So you've just seen that this channel, the single star channel, is very sensitive to the metallicity. As we go to lower metallicity environments, we expect this channel to be less efficient. Stars are not capable of stripping themselves because their winds are not strong enough. Whereas the binary channel, at least to first order, you don't really expect it to depend on metallicity, at least not in a straightforward way. And therefore, it has been suggested for a long time that as we go to low metallicity environments, to the early universe, we expect more and more Wolf-Rayet stars to form primarily through binaries and not through single stars. So what I would like to show you, and this is one of the results that we published about a year ago, is that, well, it sounds disappointing, but in fact, the answer is not at all trivial. And what was for a long time a quite solid prediction is in fact not that solid. And I hope I will be able to convey why. But before I can do that, I would like to present you the main observed populations with which we worked. And these are the Wolf-Rayet populations in the small and large Magellanic Clouds. So these are, again, these dwarf galaxies close by. They are really fantastic for providing us a sample of massive stars to study in detail at subsolar metallicity. The SMC only hosts 12 Wolf-Rayet stars. So it's a small sample, but it's also it's a fifth of the solar metallicity, so it gives us an important anchor. The LMC hosts a lot more Wolf-Rayet stars that we know of, and it has a somewhat higher metallicity content. And we have worked a lot on trying to derive the properties of these stars and understand them in the context of stellar evolution. So I won't tell you too much about the methodology of how all the results were derived, but I do want to highlight one of the main tools that we have been using and I've been using a lot in my research, and this is the Potsdam Wolf-Rayet code that was originally developed by Wolfrainer Hamann in Potsdam. It's a model atmosphere code and non-LTE, which is what you need in order to model these very complicated stars and to derive their spectral parameters like temperatures, luminosities, and so on. So again, I won't take you through the technicalities of it, but just keep in mind the sort of tools that are necessary to get the results. Another tool that I just want to mention that I used quite a lot in my research, having focused a lot on Wolf-Rayet binaries, is the method of spectral disentangling. If you've heard Laurent Mailly's talk, I guess you might know of this method. And the idea is basically where you observe a binary, you're not going to observe a spectrum of a single star, but rather this a composite spectrum containing the signatures of both components. And spectral disentangling means taking multiple observations of such a binary as they move around one another. The lines would move, spectral lines, and you can use a mathematical algorithm to disentangle the spectra and actually derive the spectra of the individual components. So these kind of methods were used, heavily used throughout my analysis and the analysis of my colleagues. And I just wanted to briefly mention them. Last thing before I jump into the results is to highlight the fact that actually one could hold a seminar almost on each of these objects individually. Each of them has their own story and each of them is a special creature. And just to give you a crazy example, this is a very recent analysis of a Wolf-Rayet star in the Large Magellanic Cloud. This is the name. It was analyzed by Sutkin Janssens in her master thesis that I supervised. And what she found is that instead of just having a Wolfray star or a binary, which is what we thought it is, she found that it's probably a quintuple. And it hosts one of the most massive contact systems that we know, as a star that looks like this and another B star. And so she could hold a seminar just on this object. But I want to focus today on the statistical properties of the population. I just want to stress the fact that all the caveats and all the things that enter the results in the background. Okay, so let's start with the first prediction that we had and that I stressed before. And this is that because the single star channel is not efficient at low metallicity and stars cannot really get rid of their wind, of their outer layers at low metallicity, there is this prediction that as we go to low metallicity, you expect to see more and more Wolf-Rayet stars in binaries. Or in other words, the binary fraction should grow at low metallicity. So the picture should, according to prediction, look something like this. In a galaxy, you might see a bunch of Wolf-Rayet stars that live alone and a bunch of Wolf-Rayet stars in binaries. And as you go to low metallicity, you would naively expect to see more and more of them in binaries. So let's see whether this prediction holds. What is actually observed? So Catherine Nugent and Phil Massey and other collaborators have actually looked into the Wolf-Rayet content of the Triangulum and Andromeda galaxies, which probe a supersolar metallicity environment. And they report Wolf-Rayet binary fraction of roughly 40% for these populations. The same fraction was reported for a long time and is still more or less holds for our own Milky Way, which also has, which has of course, roughly solar metallicity. Of course, there is some gradient, but on average, roughly solar. Then as we go to the large Magellanic Cloud, which probes a lower metallicity environment, the binary fraction, instead of growing, the reported binary fraction is actually smaller. And in the small Magellanic Cloud, which is a really subsolar metallicity environment, it again is roughly 40%. Here we have really only 5 out of 12 stars, so it's low number statistics, but this is the number that you get. So you can see that observationally, at least naively, it seems like the Wolf-Rayet binary fraction is constant with metallicity, and that could not really be understood for a long time. One thing that I would like to highlight is that these fractions are all derived with different methods by different people, and most importantly, they are not bias corrected. And bias correction is one of the most important things to do actually in this context, understanding your biases. And that's something that Karan Zilva, who is a PhD student I'm co-supervising in Leuven, is currently working on specifically in the galaxy. So I encourage you to check out his recent publication to see what he finds, but this still needs to be done systematically for all these environments. So far, it doesn't look like there is evidence for an increase of the fraction at low metallicity. And in the next few slides, I will try to explain why I believe that is the case. And this is what we have published last year. And this is not that complicated, the argument, but it's delicate. So I will try to take you step by step through the argument. And this figure is taken from the paper. What you see here is a Hertzsprung-Russell diagram with no units because it's illustrative. And I'm going to take you through this plot. So in the upper part of this diagram, we have stars that are so massive, stars that per definition, I say the initial mass exceeds a certain threshold, this M single Wolf-Rayet, that they would become Wolf-Rayet stars no matter whether they are in binaries or not. And if this diagram is too complicated for you, there is the table, the more simplistic table. A single star would become a Wolf-Rayet star, but also a binary, regardless of whether or not it's binary, it would become a Wolf-Rayet star. So actually binaries don't do much here. Yeah, they could change the details, but they are not responsible for the formation of new Wolf-Rayet stars. And we know that there is a threshold above which stars would be able to do that, and that this threshold depends on metallicity, as we have seen. What exactly these numbers are, this is the big question, but let's for now treat it as this kind of a variable. Then we have the next regime on this diagram. This is a regime where stars are less massive, not massive enough to get to the Wolf-Rayet phase as single stars. So you see a single star would become maybe a red supergiant or a blue supergiant, but not a Wolf-Rayet star. But if I put the star in a binary and it has transferred mass to its companion, I would expect it to become a Wolf-Rayet star. So you see a binary does become stripped and I would expect it to look like a Wolf-Rayet star. But you see that the mass is smaller than this as a mass single, but I also put a lower constraint on the mass here, and this is this m spec. Why do I put this limit here? What happens if I go to even lower masses? So we have many good reasons to believe that if we take stars that have initial masses lower than a certain threshold, if they are single, surely they would not become Wolf-Rayet stars. They are way too low mass for that. But if they are in binaries, you would be able to strip them, but the spectral appearance of the star, which I'm trying to kind of simulate here, would not look like a Wolf-Rayet star. So remember, a Wolf-Rayet star is a spectral type, and a star stripped in this regime, per definition, would not look like a Wolf-Rayet star. The luminosity, or rather the luminosity to mass ratio, is not going to be high enough to launch these powerful winds. And we have a lot of observational indications for this. So we know that there is a transition region where stars that are stripped will look like Wolf-Rayet stars. And the point of this diagram is that let's ask ourselves, where can binaries actually produce Wolf-Rayet stars? They cannot do it in the lower part because the stripped products don't look like Wolf-Rayet stars. They cannot do it in the upper part because single stars get to the Wolf-Rayet phase anyway. The only place where binaries really contribute to the production of Wolf-Rayet stars is this region in the diagram, which is determined by these two variables, the lower threshold for appearing as a Wolf-Rayet star and the upper threshold for entering the Wolf-Rayet phase as a single star. I hope I could convey this because this is not super easy, especially not for people outside the field. And the question is now, can we constrain these parameters? So can we constrain, for example, at which masses do stars start appearing as Wolf-Rayet stars after they are stripped? And I believe that the answer is yes, and we can do that most robustly with observations. And so here I'm showing you the observed populations of the small Magellanic Cloud, large Magellanic Cloud, and Milky Way, that probe all these different metallicities of the entire Wolf-Rayet stars that we know. The red symbols are Wolf-Rayet stars that have binary companions. The gray symbols are Wolf-Rayet stars that are thought to be single, or at least appear single. And in the Milky Way, you don't see red symbols because the binaries were not yet systematically analyzed spectroscopically. What I would like to highlight here is that you see that the Wolf-Rayet phenomenon stops below a certain luminosity threshold. There is a certain threshold where below it, we don't see Wolf-Rayet stars anymore. And this threshold is metallicity dependent. You see that this threshold is higher as we go to lower metallicity. And for a while, it was thought that this is because, well, at lower metallicity, at lower luminosity, say if we're in this galaxy here, at lower luminosities, we're not going to see Wolf-Rayet stars because they cannot form, because they cannot strip themselves. But we know that we have binaries and binary stripping. And if so, we would expect to see Wolf-Rayet stars living here in binaries, but we don't observe them. And that means that this threshold is not the threshold for when stars can strip as single stars. This is the threshold for when stars stop appearing like Wolf-Rayet stars after stripping. I hope this difference is clear. We have very strong indications for this. For example, these stars that are at the very low luminosity end, they tend to have spectra that are really close to not looking like Wolf-Rayet stars. They almost don't have sufficient winds to give them the appearance of Wolf-Rayet stars. So we know we are probing the limit of where the Wolf-Rayet phenomena actually happens. And we can translate these thresholds to thresholds on the initial masses, roughly. There are some assumptions here, but I won't take you through them. Instead, I will tell you what the results are. So in the galaxy, we estimate that stars less massive than 18 solar masses initially would not appear as Wolf-Rayet stars after stripping. No matter, even if an alien comes and sucks out their outer layers, they're not going to appear as Wolf-Rayet stars. In the LMC, this limit is about 25 solar masses. And in the SMC, it's as high as 40 solar masses, or 37. So let's say I take a 30 solar mass star, I strip it in the SMC, not going to look like a Wolf-Rayet star. If I do the same exercise in the Milky Way, it would look like a Wolf-Rayet star. Okay, so we have this already a good constraint or a good handle on the spectroscopic threshold. What we still don't know is what is this threshold? What is the threshold above which stars would be able to become Wolf-Rayet stars by themselves as single stars? And indeed, this is a poorly known quantity that depends on all the uncertainties I highlighted before about previous mass loss, mixing, eruptions, main sequence problems. So there are a lot of uncertainties here. And currently we only have to deal with the fact that we have many predictions by many different codes. And so in this table, I kind of summarize, you don't have to follow the numbers, of course, but I summarize different values for this threshold of when stars can become Wolf-Rayet stars by themselves, the single stars. And you can see the predictions vary wildly depending on the code and of course on the metallicity. But what we can do is now, using these values for each of these codes and for each of these predictions, see what do they tell us about the fraction of Wolf-Rayet stars that actually form through binaries. And the results that we get out are the following. For example, if I follow this purple curve, which represents the predictions by Dre and Taut from 2003, then you would actually, they according to this, they would predict that the binary fraction of Wolf-Rayet stars, or rather the fraction of Wolf-Rayet stars that form through binaries, predominantly through binaries, actually decreases with decreasing metallicity. That goes in the other direction of what we had anticipated before. If I take the BPAS prediction by Eldridge et al., it remains roughly constant. If I take Geneva predictions, it grows and then remains roughly constant. So this is why I said the answer is not trivial, because all of this uncertainty, but what we can see is that there is no reason to think that the binary fraction of Wolf-Rayet stars should grow as we go to lower metallicity. And that's really the bottom line that I want to make here. But so binaries don't necessarily dominate the formation of Wolf-Rayet stars at low metallicity. It doesn't mean that they're not more important for stripping stars generally, but they are not necessarily more important for forming these Wolf-Rayet stars that are characterized by strong winds. So I hope this is clear. The second thing I would illustrate briefly. So this was a prediction that at least I believe we can explain why there is a discrepancy, right? There was this prediction, then we saw there is a discrepancy with observations. I think that this is the explanation. Now we have, however, predictions that we don't observe, and I don't know what the explanation for them are. And to me, that indicates deficiencies in our understanding of stellar evolution. So, for example, we already established the fact that below a certain mass threshold, we don't expect to see any single Wolf-Rayet stars, right? They cannot form by themselves. We do expect to see them in binaries. So we would expect to see Wolf-Rayet binaries living below a certain luminosity threshold, and above it, we could see a mix of some single stars and some Wolf-Rayet binaries. And how many would depend then on the metallicity and on the details. So do we observe this picture? The answer is that no, not really. If you look at the SMC, for example, remember, we expect the binaries to be mostly below a certain luminosity threshold. We expect to see a certain threshold where stars only form through binary interactions, Wolf-Rayet stars. And above them, we should see the single stars. But we observe exactly the opposite trend here. We observe apparently single stars at low luminosities and binaries at higher luminosities. And I have no idea why this is the case. And a similar picture is observed in the LMC. It's more of a mix. But again, there is no clear cut of the binaries probing lower luminosities. And to show you how bad the situation currently is, this is for the LMC, the observed population of Wolf-Rayet stars. The colored symbols are the ones that have binary components, and the gray symbols are the ones that appear to be single. And these are state-of-the-art evolution tracks calculated by the Geneva code. And what you see is that basically none of the tracks are able to reproduce the stars that we are observing. You can only reproduce them with binary interaction, but many of those, the majority of these stars don't seem to have massive binary companions. So the question is, what is going on here? And the answer is that we still don't know. So the bottom line is that state-of-the-art evolution models at low metallicity currently cannot reproduce what we observe in terms of the Wolf-Rayet population. Finally, I would like to just talk briefly about these other types of stars, these elusive stars that live below these thresholds, so these stripped stars. Have we ever observed such types of stars? How do they look like? What are their properties? Do they agree with our predictions? So I'm not going to answer all of this in detail, but I do want to give you 2 slides on this. So this is the Wolf-Rayet population that I showed before in the Milky Way, all the stars that were spectroscopically analyzed. We do know of a type of stars that live on the very low mass end that are stripped and are hot. And these are called OB-type subdwarfs. So these are stars that really share a lot of the properties of Wolf-Rayet stars, but they are much lower mass. They're about 0.5 solar masses. And they come from intermediate mass stars, and it's really a different subject of research. But what about intermediate masses between those? So there is one object, one famous object called the Quasi-Wolfrey Star that was claimed to have a mass of 4 solar masses. But it is a really unique object and has very peculiar parameters. So I'm actually collecting some more data actually with Hermes in the hope to maybe get more constraints on it. But this is the only object we know in this intermediate mass range. And very recently, I do have to mention this, that we found potentially another such stripped helium star. It is peculiar, and I'm not going to enter the details of why, but we found that it has a mass of about 1 to 1.5 solar masses. So it's larger than the typical masses for subdwarfs. It's probably the progenitor of the descendant of a massive star. And what is this funny object? So I just had to mention it because it was such an exciting and cool project. And I know that some of you at the IAC, including Sergio, have been working on this object. So this is LB1. LB1 really struck headlines when it was reported to in nature to consist of a black hole that is as massive as 70 solar masses, which was really like a fantastic discovery and got all the community working on it. But what we found from our analysis is that this binary is in fact doesn't contain a black hole, but it is instead a binary containing a really rapidly rotating star in orbit with a stripped helium star. So exactly the type of objects I've been talking about. And we estimated a mass of about 1 to 1.5 for this star. So again, I'm not going to enter the details of the analysis, but I did want to highlight it. So bottom line, last bottom line I would like to highlight before I conclude is that we really hardly ever observed massive stripped helium stars. We observe Wolf-Rayets, we observe the subdwarfs, and then there is this crazy mass gap where we have never observed, except of maybe 1 or 2 outliers, stars in this mass regime. And there are 2 options. Either they are strongly over-predicted by current population syntheses and evolution models. We do expect many of them to exist. Or we are dealing here with a strong observational bias, and they do exist very abundantly, but we haven't been looking in the right places, or we haven't been looking carefully enough. And I think there is still a lot of effort that should be done in this respect. So I will summarize. First, I hope I could convey at least that Wolf-Rayet stars represent a spectral class, and that's an important thing to remember about them. And the spectral class means that they have very strong winds. And they come in 2 main types. The first type is the main sequence Wolf-Rayet stars, and they probe the upper mass limit, the most massive stars that we know in the universe. But the majority of them, about 90% of them, are thought to be these classical Wolf-Rayet stars, which are evolved core helium burning stars. They are understood to be the progenitors of black holes. We understand them to either form through intrinsic mass loss or binary interactions. We still don't know which of these dominate in different metallicity environments, so it's still a big problem. Binary interactions could also lead to the formation of stripped stars, and I hope that I could convey the difference between these 2 types of objects. And I would conclude with these 3 conclusions. First, I hope I could convince that the Wolf-Rayet binary fraction should not necessarily grow at low metallicity. Second, it is still not clear how Wolf-Rayet stars form, and there are a lot of problems when we compare with evolution models. And finally, there is a strong lack of intermediate mass helium stars, so helium stars with masses between 1 and 8 solar masses. So there is still a lot to be done, but I'm optimistic. We are currently really pushing our limits of what we can, looking in more populations with more instruments, and I believe we'll make a lot of advances in this field. So thank you. I'm done.
Thanks a lot, Tomer, for this beautiful talk. So now it's time for questions. So I'm gonna go through the participant list, and I see a bunch of people, at least 2, 3 people. Okay, 2 people asking questions. So I start with the first one on top of the list, which is Danny Lennon. So let me unmute you, Danny, just a second. Let me see if I can. What I can do is just unmute everyone, right?
No, haces clic sobre el...
Chatear, permitir hacer anfitrión. Just a second. No, it doesn't.
Clic sobre el micrófono, ¿no te da?
No, no me deja. A ver. Okay,
Hagan-
so I'll just go here. Yeah, let me just do it like this. Just a second. Okay. So now, Danny, you can unmute yourself if you want.
Okay.
All right, go ahead.
Thank you. Hi, Tomer. Well, nice
Hey.
talk. Can you hear me? Yeah.
Yeah. Yes.
So on this question of the binary formation channel versus single star formation channel as a function of metallicity, I seem to recall, and I'm a bit out of date on this, that there were a number of people looking at Wolf-Rayet stars and blue compact dwarf galaxies. That is, dwarf galaxies with very high star formation rates, but extremely low metallicity. Does that work give a hint as to whether the binary channel dominates at low Z, or are you aware of any work on recent work on that?
Because I focused mostly on stellar populations that we can study in detail rather than integrated properties, which I think is challenging. I do not know exactly how to interpret the presence of Wolfray stars in very low metallicity environment as the product of binaries or not, right? Because that's exactly the challenge. If you go to very low metallicity, it is very difficult to form Wolfray stars also through binaries because they're not going to look like Wolfray stars. So,
but we do see them, right, in these galaxies, right? So,
and you do see them, and then how do you know whether these are extremely massive stars that got stripped off their outer layers or whether they formed through binaries? That's exactly the point. It's not clear which of these mechanisms is more important. The fact that it's hard to make them look like Wolfray stars, or the fact that it's hard to make them strip, both of them. So it's difficult without detailed analyses.
Yeah. Okay, thank you.
Thank you for the talk, for the question, Danny. So next one asking a question according to the list is Artemio. Artemio, please, can you let me yeah, you can unmute yourself. Thank you.
Yeah, I did. Thank you. So hi, Tomer. A very nice talk as the one yesterday, by the way. So excellent.
Thank you.
I have two short questions. The first one is you didn't mention mergers in the binary scenario. Could you have a small comment? And the second one is whether you have any idea of the distribution of the rotational velocities in the Wolf-Rayets that you analyze.
Okay, yeah, two excellent questions. Mergers, super difficult because we don't know what mergers do. And for example, I don't know if I should show, maybe I should, no, I won't show the plot, but all these apparently single Wolf-Rayet stars, right? I keep saying apparently single, they appear single. They could have weird low mass companions we haven't detected, or they could be the result of mergers. And the question is, do mergers help us form Wolf-Rayet stars? And unfortunately, I'm not aware of any work that could point us to an answer on this question. We could speculate and say, yes, maybe. We could try and compare fractions of predicted mergers to the fractions that we observe. I don't think they would agree. But this is really where a lot of work is currently lacking, but where we are also having advances, recent advances, Fabian Schneider and colleagues. So I don't have an answer to this, just that it's a problem. As for the second, rotations of Wolf-Rayet stars, super difficult, because for the vast majority of Wolf-Rayet stars, at least from the spectra, you would never be able to determine the rotation because you don't see the photospheres, and you only see spectral lines forming very far from the stellar photosphere. So talking about distributions is very difficult. There are only few examples of Wolf-Rayet stars where there are constraints on the rotation. These are typically not spectroscopic, but indirect, and they tend to be very low. But I think we don't have knowledge of distribution that one could compare in detail to evolution models, for example.
Thank you.
All right. Thank you. So next attendant asking a question is Sergio. Sergio, you can activate your audio.
Yeah. Thank you very much, Tomer, for this great talk. It put together some pieces on my mind that were disconnected, so I learned a lot. So as you know, I'm now mainly concentrated on the main sequence evolution of these massive stars, and as you've shown, before going to the Wolf-Rayet, these stars are going to pass through the region of the main sequence, either to become the Wolf-Rayet or the street stars, no? So what do we know about the amount of time that these stars going to the Wolf-Rayet spend on the region where the main sequence stars are? And do we have, or what do we expect to see there in this pre-Wolf-Rayet or pre-street star?
Yeah, very difficult question. If I take for example a textbook evolution model that becomes a Wolf-Rayet star, like a BPAS model, then it would evolve to it evolves to some kind of a red or blue or something supergiant, and then it stays there for a while. But there is a very sudden moment where it basically it escalates the process, and the star very rapidly goes to the left. So in principle, we don't expect to see many stars going on the way to becoming Wolf-Rayet stars, but observationally, we do observe many Wolf-Rayet stars stuck in this intermediate regime, and some of them have hydrogen, so maybe they are inflated. And there are all these different speculations. Some of them are stuck as blue supergiants, right? And this is something that concerns you a lot as well. Are they core helium burning stars? Are they core hydrogen burning stars? So it's I don't have a good answer to this. I don't have a
probably will be from the observation. No, at some point we will find weighted stars in this domain, and we can connect.
Exactly. I think the main challenge right now, we know that there are a lot of stars in this region, is intermediate region, kind of stuck in the main sequence. And I think it's still very challenging to say, are these core helium burning stars going on the way to the left? Are these hydrogen burning stars? Sometimes it's clear, sometimes it's less clear. And that's why it's difficult to talk about statistics in this sense. Yeah.
But in principle, from the models, this is very fast. So it's not that you have an intermediate region where they stop.
No, it's very fast, and then from the models they should get stuck as very hot stars for most of their lives, stuck on the helium burning main sequence. But that's not what is observed indeed. Why is a different problem.
Okay, thanks.
Thank you, Sergio. So next one talking is asking a question is Miguel Cerviño.
Hello, well, very nice talk. I have two comments. Well, one question and one comment. Well, the comment is about the naked, about discrepant stars. I have read something more than 10 years ago that, how you look for in planetary nebula, because there is a lot of people working with planetary nebula, and there is Wolf-Rayet C type in planetary nebula. That Wolf-Rayet C, this kind of binary discrepant stars, there will be Wolf-Rayet C if there is Wolf-Rayet at all. There is they cannot be Wolf-Rayet N. Must be carbon Wolf-Rayet star that goes to planetary nebula. Well, it was the comment, I don't know. And also the question, you talk a lot about the binary fraction, but this is not exactly the real interest quantity, because the quantity is the fraction of interacting binaries. So when you talk about this 40%, it is the upper limit, but it doesn't tell you nothing about the formation of Wolf-Rayet. You need to know what is the number of the fraction of interaction that is there. So for the large Magellanic Cloud and for the small Magellanic Cloud, have you tested how many of these binary stars can be interacted or not?
Yes.
Or not?
Okay, so I have to comment on also the comment and also the question. To me, both were questions. As for the low mass Wolf-Rayet stars, which I haven't mentioned at all on purpose, in fact, they also follow this. Wolf-Rayet stars are a spectral class. It also corresponds to them. They're a different type of Wolf-Rayet stars, low mass Wolf-Rayet stars that are our sun might become an object like this. I am very familiar with them. I am working with people on them, but they represent a different class of objects and low mass objects. And it's confusing because low mass objects, it's also a research how exactly it happens, but when they do get to this phase, they can appear as Wolf-Rayet stars. They develop these powerful winds. Then in intermediate mass, we have many reasons to believe that they don't develop these winds when you strip them. So if if you start stripping the masses that I talked about, you don't enter the regime of Wolf-Rayet. You don't launch these winds. And it's only again when you enter the very high mass end that you start launching the winds again. So I'm very much aware of these objects. And as to the second question, a very good point. So what I didn't talk about at all is how these fractions were derived. And in all cases, these fractions are, with the exception of a few outliers, spectroscopic binaries. In other words, close binaries. We're talking about binaries that in the vast majority of cases could interact. Whether they have interacted, difficult question, but we're talking about close binaries. So orbits of a few years or less. These are these fractions. If I start talking about gigantic scales, then these fractions could be much larger. So I don't think it's a lower limit. I think it's more of a representative limit, but like I said, bias correction should be done. And so that's a good point, should be thought about.
Very well. Okay, so apparently thank you, Miguel, for your question. Apparently the last question is from Miriam Garcia. Miriam, you can go ahead.
Hi, Tomer. Thanks again for the talk. You've alluded, speaking about luminous blue variables. That was very smart. But I was wondering if we might find any kind of clue as for the intermediate mass range and all this Wolf-Rayet the models are not predicting. Yeah. Could you comment on that?
Yes, I've avoided them on purpose because you cannot talk about Wolfray stars and yet talk about luminous blue variables could well be the answer to the problem that we are facing with reproducing the apparently single Wolf-Rayet stars at low luminosities, right? They are not reproduced by current models. And then the question is, if you put an LBV that starts erupting mass at lower masses, could you then strip the stars as single stars? So the thing is, interpreting it naively could suggest that the classical scenario of Conti, O becoming LBV, becoming Wolf-Rayet, that this is the correct scenario. But there are still other ways to resolve this. Mergers, common envelope evolution, mixing parameters, other things. So from the Wolf-Rayet perspective, it's still difficult to put a constraint on an unambiguous constraint on the LBV question, I'm afraid. But it's part of the puzzle. So.
All right, thank you.
Thanks.